In this lecture, we're going to go over looping structures in MATLAB. So first we're going to look at some algorithms with looping structures to really understand what these loops are accomplishing. The learning objectives that we're trying to achieve are to create a written algorithm that utilizes indefinite loops when applicable to solve an engineering problem, to sketch a flowchart that implements indefinite loops, to generate an approximate set of test conditions for all possible pathways through our algorithm, to create a written algorithm that utilizes definite loops when applicable, a flowchart for definite loops, and to generate an approximate set of test conditions for our definite loops. So there's two different types of loops we're going to look at. We have indefinite and definite loops. So the two types of loops that we are looking at again are our indefinite, which are conditional loops. These are our while loops. So a segment of code executes as long as some condition remains true. And then we have definite loops, or our counted loops, and these are our for loops. So a segment of code executes a known number of times. Indefinite while loops, so they're executed until a specific condition is false. Applications of while loops are for data validation. How do we know the user is typing a number greater than 0? How do we know the user is typing in a 3x4 matrix? For control, so it gives the user the option to run a program again after it completes. We can also use it for error minimization, so we can execute a segment of code repeatedly until it's acceptable enough to report a final value within a specified error range. So what does a flowchart for an indefinite loop look like? Well, we have our initial variables, we have the condition for repeating the loop. If the condition for repeating the loop is met, we proceed the process that includes changes to the variables and being checked, so we're running our loop. We go back, we ask the question again, and we keep going through this circle until this is no longer met and our program will continue on. So for example, we're going to look at our phase of liquid water again. So we want to create an algorithm to determine the phase, and if the temperature is outside the physical limits, we want to ask the user to enter a value until the user enters a valid temperature to be used. So most of our algorithm remains the same from the previous examples that we have looked at. We know the temperature input by the user, the output is our phase, we have our variables that define the limit of our phase. We also have the variable that defines the physical limit of temperature. So what can we do? What does this look like in a flowchart? Well, we would have our set our inputs, we would have the user input the temperature, and then we would ask, is our temperature less than our limit? Just like we did when we had our logic version of this example. Only this time, if it is less than the limit, we give them a warning message and we ask them to re-input it. So this is where our loop is occurring. Whereas previously, if they input an incorrect value, we just told them, nah, that value is bad, give me a new one. Oh, that value is bad. And the code ended. If the value of temperature that they give is not lower than our limit, it will execute the following segment of code to determine the phase. So the loop is occurring here in red. So test cases that we would need are test cases that are less than our limit, so like minus 500 degrees Fahrenheit or minus 1,000 to make sure we get the output of invalid entry, try again. A similar thing can be done with the blood pressure example that we looked at previously as well. This time we're going to, if the user inputs an age range that is unacceptable, so if it's not between 15 and 24 years old, we then want to prompt the user to input an appropriate age. So again, the main parts of the algorithm that we wrote last time are the same, where we have our known inputs of the age of the user, the systolic and diastolic blood pressure, and we have our ranges to use for our conditional statements. What's new, and it's a little hard to see with the written algorithms, but what's new is this part in red where we are comparing the input from the user to our age mins and max to make sure the age that we are given is in the right range, where if it is, it will warn the user that they have entered an invalid age and go back to step 2. If no, it proceeds on to step 4. So here again in red, this is the loop that we are adding. You input an age, we ask if it's correct, if we ask if it falls outside of our range. If it falls outside of our range, we prompt the user to do it again, and this would keep going and going and going until the user inputs a correct age number, which is why it's called an indefinite loop because this loop can run forever. So you do have to be very careful with the conditions that you write for your indefinite loops, because you could create an infinite loop that just keeps going on forever. In this case, we would also want to make sure that we test it for an age less than our limit and an age greater than our limit. So we have a test case of 9 and 40. All right, so now we're going to look at definite loops. These are for loops. So they execute a specific number of times. Application for for loops include basic operations. So if I wanted to do a repeated operation on each element of our matrix, for example, how we were finding out that logic won't be considered for each element. And then sampling. Say I want to take every 5th measurement of my sample. So what does a flowchart for a definite loop look like? So we still have our initial values. We set our initial counter. We ask if our counter is less than the max. If it is, we proceed within our loop and we increase the increment of the counter by 1, and this keeps going until our max limit has been reached. And then we continue the program. Note, if the increment is negative, the question should be asked if it is greater than or equal to, not less than or equal to. So it gets a little tricky with how you want to phrase your logic. So for example, without the aid of the sum command, I want to sum all the values of this vector and then print the sum. As a test case, we're going to use v is equal to these two cases. So what would happen in the first one? So what are we asking? I want to sum all of the elements in these vectors without using the sum function. So an intermediate variable that I probably would need is the length of my vector. How would this look like in a visual flowchart where I would input my v? I would calculate the length of my v. I'm going to set my counter to 1, and I'm going to set my sum to 0. So I'm going to pre-create my variables. And then I'm going to say that my sum is equal to my previous sum plus a v of I. So I'm going to use my counter as an index. And then I'm going to ask, is my sum greater than my length? If it is not, I'm going to add 1 to my counter. I'm going to go back and now add the next element of v back to my previous sum. And I'm going to keep executing this pathway until my counter is greater than L. If my counter is greater than L, I have completed my loops and I will print S. So we want to assume that we have 2 row vectors, A and B. They're of equal length. We want to write an algorithm to evaluate these matrices element by element. So we want to create a new row vector C based upon the following conditions. So previously we really couldn't do this because the logical variables that we were creating didn't necessarily allow for multiple cases to occur. It also didn't look at every single element sometimes. They were trickier to use, but what we could do is create a loop to accomplish that. So what would I do? I'd have my 2 vectors, vector 1, vector 2, and a sub variable, which would be the length of my vector. You're using the length of your vector to count how many times to run through your loop to make sure we do our calculation on every single element of our vectors. And we want our output to be the evaluation C, again, based on the logic. If they're equal, put 0. If their sum is greater than 0, put 1. If their sum is less than 0, put -1. So the previous logical variables only created 0s and 1s, so this third condition would be a little tricky to evaluate. So what does this look like in terms of a visual algorithm? Well, we would start by inputting A and B. We would find the length of A or the length of B, since A and B are the same length. We would set our counter to 1. We would ask, is our counter greater than L? If it's not, we would then ask, is A of 1 and B of 1 greater than 0? If it was yes, we'd say C of 1 is 1, and we would go through to add 1 to the counter. If it was not, we would then ask our second piece of logic. Based on the result, we would get our -1 or our 0, and we would go back and we would keep going through this loop as many times as needed until I was greater than L, so until we have performed this calculation on every element in our vector. So we're going to ask the user to enter a random value. We're going to create a loop to replace that value with the sum of the square root of that value. We're going to repeat this process until the resulting value is within 1% of the sequence limit, or the process has executed 5 times. So what do we know? We're going to enter a random value by the user. We don't need any intermediate values. And then the output is the average calculation, the ending calculation, and the number of times the program has been executed. So the assumption that we're making is the user must enter a value whose square root function will approach 1, which basically means we can't have any negative numbers or 0. So what we do? Well, we're going to ask the user to enter a random number. We're going to ask if that random number is less than 0, because if it's less than 0, we're going to say, well, there's no possible solution. We're going to end. If yes, if no, which means we have our positive number, we're going to proceed to step 3, which is set n equals 1 and m equal to mi. And then we're going to calculate the square root of m and store it back in m. And then we're going to ask if the absolute value of m minus 1 is less than 0.001 or n is equal to 5 to calculate this loop. If this is true, our code would end. If this is true, we'd proceed with the number of loops as many times as we needed. So if it was true, then we're either printing mi, m, and end and ending. If not, we're adding 1 and going back to step 4 and continuing this until n is equal to 5. Where would this look like visually? We have our input. We're making sure our input gives us a valid response, because if not, we're going to print an error and end. If it is a valid number, we're going to set n equals 1, perform our calculations, ask some logic to see if we are ending our loop or not. If not, we're going to add and keep going. If yes, we're going to end and print it. So some test cases would be if m is equal to minus 5, nothing is going to occur. If mi is equal to 0, again, nothing is going to occur. If mi is equal to 5, we're going to print, these are the values in every iteration. At 5 iterations, it will stop, and it will give us the value that we were calculating at, and that n is equal to 5. In the second test case, it only runs 4 times because we have reached within our % error, and same with the final one. The reason we have 4 test cases is we want to make sure it's within a positive and a negative 5% of our 1. So far I've mentioned that we have these 2 different kinds of looping structures. We have indefinite loops, which are called while loops, and we have definite loops, which are called for loops. And I kind of explained how they work and what their structure is. Now we're going to actually look at how to define one in MATLAB. So we're going to create the conditional indefinite loops in MATLAB. We're going to calculate the number of executions of an indefinite loop. We're going to initialize variables tested in an indefinite loop. We're going to restart a program using an indefinite loop. We're going to use an indefinite loop for input validation, and we're going to use an indefinite loop to terminate interval solutions. So we're just going to look at how we can use indefinite loops. So what does an indefinite while loop look like? Well, you have the initialization. First, you have the initialization of your loop variables. Then you have while, which is going to begin our loop, and after our while statement, we're going to enter our logical expression that will keep the loop running. Then we have our executable code, and once we reach the end of our executable code, we enter our end function. So we have our while and our end to bracket the 2 pieces to bracket the code that's going to run while we are in this while expression. Some notes are that all variables used in the logical expressions of the while loop must be initialized prior, so you have to have all of your variables defined before, otherwise you're going to overwrite them every time your while loop runs. The syntax of a while loop is nearly identical to an if statement. The executable statement should be able to change at least one of the variables within the logical expression, otherwise your loop will never end. So let's write a short section of MATLAB code that will ask the user to enter their desired value of a magnetic field strength in teslas. If the user enters a value of 40 teslas or greater than less than 40 teslas or greater than 80, we're going to put an error message in that this is not valid, try again. And that should appear on the screen, and then re-ask the user to input a value. So what is this going to look like? Well, first, before we even start our while loop, we have to ask our user to input a value of magnetic strength between 40 and 80 teslas. Then we're going to make a while loop, and For the condition we're going to use in our while loop is if b is less than 40 or b is greater than 80, we're going to print that this is not valid to try again, and then we're going to reprompt them to input the magnetic strength in Teslas. And this 2 lines of code would keep running until this while loop is satisfied. For example, isn't satisfied. So until b is greater than 40 and less than 80. So we're getting in that range that we wanted. So it's very similar to the if statements that we were working with previously. When a while loop isn't triggered, so when we're getting the numbers that we want, the while loop will end and we will print our desired field strength. Here we are again back at our example of the phase of our solid, liquid, and gas water. We're going to make a while loop to do this. So what are we going to do for this algorithm? So the first thing we need is to set our liquid limit, our solid limit, and our temperature limit. So we have our 3 constants to use. Then we would prompt the user to input their temperature in Fahrenheit and store it in a variable t. Then we want to compare the value of t to the limit. If t is less than the limit, we want to warn the user that the temperature is too low, and then reprompt them to enter a new temperature. If t is greater than the limit, we don't want to run this while loop, so this will not trigger. And then we can have our if statements to figure out our phase like we did previously. So what we added are these 4 lines of code here to trigger a warning to keep the program running, whereas previously we had an if statement there, and if it was less than the limit, the code just told them you put in an invalid answer and ended. Here we want to write a MATLAB code segment that will allow the user to type numbers into the command window. Your code should count the number of positive and negative numbers typed by the user. Note that each time the user types a number, it's followed by the enter or return key. That is, the user is typing 1 number at a time. The code should run repeatedly until the user enters the number 0. After the code terminates, the following output should appear that you have typed XX positive numbers and YY negative numbers, where X and Y are replaced by the numbers that the number of times a positive or negative number was input. So what might this look like? Well, first we're going to start with some random number. We want to make sure that it's a random number that triggers our loop. We're going to set p equals to 0, so positive is 0 and negative 0. So we're going to set p and n to 0. So then we're going to ask while I is not equal to 0, because we want any value but 0. I is then equal to the input, and we're going to ask the user to type a number. The reason I is defined outside of the while loop is because if I was defined inside of the while loop, the while loop would never trigger. Could you have prompted the user for a number to begin with? Yes, but what if the user typed in 0 and then then the whole code would never run. And then based on that value of I, we want to know if I is negative. We're going to add 1 to our negative counter, which is n. If I is positive, we're going to add 1 to our positive counter, p. The first end ends the if statement, the second end ends the while statement, and the while statement will end when I is equal to 0, since that is the logic we are using. And once that's done, it will then type the statement that the problem had asked us. So what about for loops? For loops are our other set of loops, and they're the definite loops, so they only run a fixed number of times. So we're going to figure out how they work and learn how to count how many times these loops run. We're going to use counter variables to index arrays. We're going to understand nested for loops. We're going to use index notation in matrices and nested for loops. So again, as a reminder, a for loop executes a fixed number of times. It's great to use with matrices and sampling. So for the syntax of a for loop, we have for, and then after for, we write the variable that is our counter, and it is equal to the start, step, and finish. So remember way back when we learned about linear sequencing, this is where linear sequencing really comes in handy with using the colons to determine your step size. You should note that while a for loop will run for while a for loop will run for a counter that's not an integer, it will cause problems if you are using a for loop for indexing, because you can only index integers. Another big thing is that although many languages commonly use I and j as index variables, you really should avoid this in MATLAB. A lot of people don't, because MATLAB uses these as a predefined version of the square root of -1. So unless you're really doing a problem that involves the square root of -1, you won't run into a problem, but it is an issue that you should be aware of. The start, step, and finish can be variables, numbers, or expressions. The step is also called the increment. Finish is also called the stop. So you shouldn't modify the counter inside of the loop, because if you do, you're going to screw up how many times your loop is supposed to run. And you do not modify any variables in the start, step, or finish inside of the loop either, because again, you're going to break your loop. So we're going to look at how we can use a loop to make a numerical sequence. So we can display the numbers 1 to 10 as follows. We can say for k equals 1 colon 1 to 10, print the value of k, and that would count from 1 to 10 in our integers. If we want to display 10 to 1, we can say for k equals 10 minus 1 to 1, so it can count backwards as well. So a for loop is just executing a sequence a fixed number of times, which is why you have to be careful. It will just set this value of k based upon this linear sequencing. So they don't have to be integers, but if you're using this for indexing, they do. So let's look at a for loop tracing example. So what is the output of the following code? We have q is equal to -5. I want to print q, put a tab, and then put a new line for n. So for n is equal to 3 in steps of 2 to 7, we want to print the value of q, then the value of n, spaced with a tab, and then going to a new line. And then we want to say q is equal to q plus 1 plus n. So let's see how this works. First, we have q is equal to -5. So I'm going to print q and I'm going to print n. Next, I want to say n is equal to 3. I want to print the value of q and I'm going to print the value of n. So then I'm going to add 1 to q plus n, so it's -5 plus 1 plus 3, and I'm going to restore that value in q. So then I'm going to go back to the beginning of my loop, and now n is equal to 5. So I'm going to print my new values, which are -1 and 5. I'm then going to add 1 to q plus n again. So I'm going to add 5. I'm going to add 6 to my value of q. I'm going to go back to the beginning of my loop. N is now equal to 7. So I'm going to print the new value of my q and the new value of my n. At this point, I'm going to go back and I'm going to add 1 plus n to q. But when I go back to update n this time would be 9, which is greater than 7. So my loop ends, and this is the final output from that code. Please note that the value of q is still updated even though it has not been printed. So let's look at another one of, we want to print the value of q and n, and this time we're going to print it after we update it, not before. So we're going to start our code, we're going to go execute our print command, and then we're going to add 1 plus n to q, and we're going to print those values. And then we're going to go back to the beginning of our loop, and then we're going to print q and n again, because this print command statement is now inside of the for loop. We're going to add 1 plus n to q, and then print those values again. Then we're going to go back through the loop another time, print q and n again, and then we're going to print the value of q and n one last time. At this point, if we add 2 more to n, we have 9 again, and our loop will not execute any further. So we're going to look at another example of tracing a for loop. We have v is equal to 20 minus 8, 3 minus 3 minus 2, 50. We're going to say the number of positive is 0, the number of negatives is 0. We have a for loop that says for x equals 1 in steps of 1 to the length of v. If v of x is greater than 0, we're going to say the number of positives is equal to the previous number of positives plus 1. And the positive vector that we're going to create of that index is equal to v of x. Else, we're going to add 1 to the negatives and create a negative vector of just the negative values. So what happens when we trace through this code? Well, we're going to look at the variable v, the number p, the number n, x, positive, and negative. So we're going to look at all of our variables. So the first time we run this code, we have our v, which is never going to change. The first time we run it, we're going to have np is 0, mn is 0, x is equal to 1. And if x is equal to 1, we're going to ask if v of x is greater than 0. Since v of x is greater than 0, we're going to add 1 to our positive number. And then we're going to say the positive of 1 is the value of x of 1, which is 20. Then we're going to end that if statement. And we're going to go back into our for loop because our for loop hasn't ended yet. So now x is equal to 2. We're going to ask if v of 2 greater than 0. Since v of 2 is not greater than 0, we're going to go to the else part of our statement. We're going to add 1 to the negative number, and then we're going to store that value in our vector called neg. We're going to end our if statement. We're going to go back to our for loop because 3 is not, we haven't reached the length of our vector v yet, so x is now equal to 3. We're going to ask ourselves if v of 3 is greater than 0, which is, so then we're going to add 1 to the counter for positive. I'm going to store that value in my positive vector. I'm going to end my if statement. I'm going to go back in my for loop. X is now equal to 4. I'm going to ask if v of 4 is positive or negative. It's negative, so I'm going to add 1 to my negative counter. I'm going to store that value in my negative vector. I'm going to end my if statement. I'm going to go back in my loop again. So x is now equal to 5. I'm going to ask if the fifth element of v is greater than 0. It's not. So I'm going to add another 1 to my negative counter. I'm going to store that value. So I'm going to go back through, and now x is equal to 6. I'm going to ask if the sixth value of x is greater than 0. It is, so I add 1 to my positive counter. I store that value. I end my if statement, and this time if I add 1 to x, x would be equal to 7. So now the code is complete. So when the code is finished, these are the values of the variables that we are going to have. Back to the previous example, if we're trying to not use the sum command to add up all the variables in our vector, we had written an algorithm to do it. How it would look in code, we would have our vector v, we would say sum is equal to 0. We would create a for loop which goes from 1 to the length of v. Remember, if we don't put a colon in between the start and the end, MATLAB defaults to steps of 1. We're going to say sum is equal to our previous sum plus v of our counter, and that will add up all of the elements. We want to write a short code segment that's going to modify our vectors v1 based on the following guidelines. We want each element of v2 that is greater to leave the value unchanged. If each value is less than 1, we want to change it to a -1. And for each element that has a magnitude, we're going to put zeros in for values between it. So we're going to start by initializing our vector. And then we're going to say for k equals 1 to the length of v2, because we want to perform this operation on every element of v2. We're going to say if v2 is greater than or equal to 1, the modified vector is equal to the value of v2. Else, if it is less than or equal to -1, we want to put in a value of -1. Else, if it's not equal to either of those, basically if it's 0, we want to put in a value of 0. So for loops are a way that you can have logic performed on multiple elements within a vector or matrix without using logical variables and making sure that it checks every single element for something that you want. So now we're actually going to trace a nested for loop. So we're going to print n and m, and then we're going to work our way through this loop. So the first thing we're going to do is print them. So next we're going to have for n equals to 1, then we're going to have m is equal to 12. We're going to print the values. We have 1 and 12. And then we're going to keep going through this loop. So I'm now going to subtract 4 from 12. I want to have n is 1 and m is 8. Notice n does not change because I'm not exiting the inner for loop yet. So then I'm going to go back again and subtract 4 more from 8, which gives me a value that is less than 6. So I'm going to then exit the inner for loop, go back to the outer for loop, and this is going to set n equal to 2 and then m equal to 12. Then I'm going to go through the inner loop again. Then I'm going to exit the inner loop, go back to the outer loop, set n equal to 3, go back into the inner loop and set n equals to 12, execute my print command, go back through it, set n equal to 8, execute my print command, exit my inner loop, go back to my outer loop, and at this point, adding 1 to n, I hit my 3, I'm done. The entire code is going to end completely. So we're going to try and figure out what is stored in m when the following code is finished. We have m is equal to 10, 20, 30, 40. Nested for loops are great for doing indexing with matrices because you have rows and columns. So we're going to get r and c, which are the size of m. So we're going to go for little m is equal 1 in steps of 1 to r. So for all the rows and for all the columns, we're going to create a new vector that is our previous one divided by 5. I'm aware this could be done without a loop. We're just going to look at what a loop does. So here's our original matrix of 10, 20, 30, 40. First, we're going to have I equals 1, j equals 1. So we're going to get m of 1, 1 is equal to 10 divided by 5, which is 2. Then we're going to get I is 1, j is 2. So we're going to do 20 divided by 5, which is 4. Then we're going to get I is equal to 2, j is equal to 1. So we're going to have 30 divided by 5. And then we're going to have n and m are I and j are equal to, it was m and n, not I and j, my apologies, are equal to 2, so we're going to have 40 divided by 5. Nested for loops like this are great for performing a calculation on every element of a matrix. So we're given a square matrix. We want to determine the sum of the elements that are equal to the corresponding elements of the transpose. We want to note that all of the elements on the main diagonal will be included in the sum, and this may or may not be all of the elements in the sum. Our code should implement this with nested for loops, even if you know how to do it without loops. We're working with loops right now. The elements that are in the sum are circled in this case, and the result is -10. So what do? We define our original matrix. And then we get the row, we need the number of rows and the number of columns. We're going to set our sum equals to 0, and then we're going to set our second variable. We need the transpose to the transpose of our original matrix. So how are we going to set this up? We're going to say, well, for row equals 1 to the number of rows, and for column equals 1 to the number of columns. SM of row and column, if SM of row and column is equal to SM transpose of row and column, sum T is equal to our previous sum plus the value of SM of that row and that column. So this is where we're really using indexing within these for loops to perform calculations. So in this case, we're given a matrix M1. We want to create a column vector nor P containing the same number of rows as M1. For each row of M1 in which the sum of the positive elements is greater than the sum of the magnitude of the negative elements, the corresponding element in nor P should contain a 1. And if it's negative, we want a -1. And if it's equal, we want a 0. So what are we going to do? We're going to initialize our M1 matrix. We're going to determine the number of rows and columns using our size function. We're going to initialize our variable nor P so it exists prior to entering our loop. And then we're just going to go through it element by element. We're going to start with the number of rows. We're going to set our sums to 0 because we want the sum for each row to be 0. If we had set the sums to 0 inside of the second for loop, they would not reinitialize when we go to a new row. So then we're going to go through all of the columns. We're going to ask, is my value less than 0? If it is, I'm going to add it to the negative. If it's not, I'm going to add it to the positive. And then once I've added these, I want to say, is is this negative sum less than the positive sum? And if it is, I'll put a 1. If it's not, I'll put a -1. And if they're equal, notice this last if statement will not run, so we would get a 0. Then I'm going to go back and update the number of rows and do it all again. So that's it for looping, and looping is a very specific thing to MATLAB which does come in handy, which allows you to perform calculations on elements, keep a code running for a specified number of times, or to extract data, or to get to an error that you need by using a while loop. While loops can be very tricky. You do have to make sure that the logic you're opposing will not create an indefinite loop. If you do, you can always hit your Control-C to end that. The next topic we're going to look at is graphing, and we're going to start with graphing in Excel.